Chapter 6, the skeletal system, bone tissue. The functions of the skeletal system. The skeletal system has 6 important functions. These functions include support. The skeletal system provides a structural framework. If you think about your rib cage, your pelvic girdle, all protecting your heart, your lungs, your genital organs, etc. We have storage of minerals and lipids. So those cavities within our bone, those medullary cavities, is where we're going to have our bone marrow, red bone marrow, yellow bone marrow, where we're going to produce cells, which is our next function, but also store fats and certain minerals. Next, as we just alluded to, blood cell production, which is called hematopoiesis. So our red bone marrow is where we're going to find our pluripotent stem cells that's going to differentiate and give rise to all our various blood cells. Next is calcium regulation. So 99% of the calcium that we get in our body is stored here inside our bones. The 5th function is going to be protection. So again, we are protecting organs. So this kind of aligns with our structural framework that we are forming the shape of our body, as well as protecting important and delicate organs, again, like your lungs, your heart, your genital organs, your reproductive organs, etc. The last one, I know it's cut off here, but it is leverage or movement through our articulation. So again, articulations is a word we're going to use again and again, which means jointing. So we look at your arms, your legs, your head, your neck, your ribs, your vertebra, all these connections where bone meets bone is forming a joint. Right? And we're able to move these joints through various movements, so like flexion, extension, abduction, adduction. And we're going to go through this again later on in the subsequent lecture. Let's look at the structure of a bone. So a long bone is what we're going to focus on, is going to consist of several parts. The diaphysis, which is essentially the longest part of this bone, or the shaft. 2 epiphyses, so these are the ends of the bones, a proximal and a distal epiphysis. This is usually covered with our articular cartilage, which is going to allow for a bone-to-bone connection. 2 metaphyses, so these are the region meta, meaning between, the region between the diaphysis and the epiphysis. And then we get this articular cartilage. This is what covers the epiphyses. So again, this smooth hyaline-like cartilage that is producing a slick surface. Now, I usually tell my students at this point, if you've ever had a chicken leg, if you've ever eaten a chicken leg and you look at the end that you hold on to and you see that it's smoother and shinier and more white than the rest of that chicken leg bone, that is the articular cartilage. Next is the periosteum. So again, here's our terminology. Peri meaning around, osteum meaning bone. So it is the connective tissue that surrounds the diaphysis. Now, if we go to the inside, and we used this word before, we have the medullary cavity. This is a hollowed out space that is within the diaphysis. This is where we're going to find the majority of our yellow, or some places you'll see pink, marrow. Now, lining that medullary cavity, we have an endosteum. So endo meaning within, again osteum meaning bone, again thin membrane lining that medullary cavity. We're going to get back to the structure of the long bone, but before we get into too much detail, let's classify our bones based on shape. So we've already introduced a long bone. Now a flat bone is, as it implies, flat. A short bone, again short. Irregular will have an irregular shape. A sesamoid will have a sesame seed shape, and a sutural bone is a bone that forms these zipper-like connections or sutures along, say, our cranial bones or facial bones. Let's put it to picture. Let's classify these bones. So we see short bones are going to be your wrist bones, your carpal bones. Flat bones, like your cranial bones, like the parietal bone on the top portion of your head. Long bones are humerus. Here's our sesame-shaped sesamoid bone. Look at that vertebra, irregular shaped. It's not long like this. Humerus is like a long bone. It has all these different projections and regions. So irregular shaped bone. And then again, we go back to the cranial bones and we see all these zipper-like structures, these sutures that connect all these flat bones, so sutural bones. When we look at the two types of bones, in our histology lecture we talked about compact bone, how it's dense, glossy, bright, and then how the basic unit is that haversian system, or that osteon, the central canal where all those blood vessels come through. And then we talked about those perforating Volkmann canals, which are going to extend between those adjacent osteons. These perforating canals provide energy and nourishing elements for those osteons. The second type of bone is called spongy bone. This is typically found in flat bones and towards the ends of our long bones. They are made up of this open network, a strut of bones. We call these struts trabeculi. They are a little bit different from compact bone, where they do not have a haversian system. There are no osteons. Now we're going to spend some time focusing on a typical long bone. So we put this slide in as a review, as a repeat of some of the major portions. So we start again with the diaphysis, the shaft. We have the proximal and distal end of the epiphysis, or the epiphyses, which is made up mostly of spongy bone, where we're going to find the majority of our red bone marrow. The metaphysis is the middle portion. It is where we're going to find our cartilaginous plate, which is reduced to a line at puberty. So when we talk about our growth plate, where our bones are growing, this is typically where it occurs. Our articular cartilage, again, that hyaline-like cartilage, there's more water and it's very slick. That periosteum, which is going to isolate bone from the other tissue, it is that connective tissue that surrounds the diaphysis, is made up of these Sharpie's fibers, which are collagen fibers from tendons and ligaments that connect to the periosteum. So we're forming that connection of muscle to bone. Now the periosteum has two layers. It has a fibrous layer. This is what blends with tendons and ligaments, allows for bones to make that firm attachment to their muscles so that we get that movement. The second layer is a cellular layer, and this is what's involved with growth and repair. Now as we move to the inside, that medullary cavity is lined with an endosteum. It is an incomplete layer of osteoprogenitor cells. These are stem cells that give rise and form our osteoblasts, so our bone building cells. The endosteum lines the marrow cavity and the central canal of our osteon. Lastly is our marrow cavity. This is where we're going to find our different types of marrow. So we have red bone marrow, which is our blood cell formation, so our site of hematopoiesis, or where we're forming all our different red blood cells, white blood cells, and platelets. We have our yellow or pink marrow, which is essentially adipose tissue. It's lipids. It's where we're keeping an important energy reserve. Now, typically, red bone marrow is going to be found between the trabeculi of the spongy bone, and again towards the end of long bones and within flat bones. Now let's put it to picture. So we have here a humerus, this is our arm bone, and we can see some of our macro portions. We have our proximal, so again this is closest to the joint, proximal epiphysis, our metaphysis, and in that metaphysis we see here's that growth plate, it is closed, that epiphyseal line. We have our diaphysis, our distal metaphysis, and distal epiphysis. Notice the shiny blue glossy hyaline-like cartilage of our articular cartilage. Peeling away this membrane right here is our periosteum. Then we get this hollowed out space. This is our medullary cavity. And again, you can see another blue peeled layer right here, our endosteum. Now, on the outside, shiny, glossy, yellow, compact bone. Towards the ends of our bone, spongy bone, which is going to contain our red bone marrow. And again, at the other end, this blue glossy appearance at the end is again our articular cartilage. Let's look at the histology of bone. So bone's going to contain 4 types of cells. We already introduced our osteoprogenitor cells. These are those bone stem cells that are able to differentiate into the other types of cells, specifically osteoblasts. Now our osteoblasts, if you think about osteobone, blast meaning building, are our bone building cells that are going to secrete the collagen matrix that's going to help build this bone. Now, osteocytes are going to be our mature bone cells that are going to help maintain that matrix once the bone has been laid down and ossified. The next is our osteoclasts. So osteobone, class meaning destruction. These are kind of like the Zambonis, and I use this as an analogy because it helps us understand what it does. If you think about a Zamboni that goes and scrapes away and melts the top part of the ice as it paves and allows for new ice to be laid, and it goes up and down in this zigzag fashion across the entire ice skating rink. Well, that's what osteoclasts do. They kind of zoom across and grind away and destroy bones. So they remodel bones and cause them to release calcium, allowing for those osteoblasts to lay down and remodel and put new bone. So let's take a look at some of these cells and what they give rise to. So our osteoprogenitor cells develop into an osteoblast. The osteoblast forms the bone extracellular matrix, so lays down those collagen fibers, and then differentiates into an osteocyte, which is there to maintain and monitor that bone tissue. Then we get our little Zamboni. Again, this is our osteoclast. Look at that ruffled border. It kind of helps to think of it like a Zamboni, right? With this ruffled edge that scrapes along the ice and then melts and then paves a new ice path behind it. So osteoclasts do the same thing. They function in resorption of that bone matrix by breaking it down. So the breakdown of bone from that extracellular matrix. Let's take a look at a real bone so we can identify and see the difference between compact and spongy. So compact bone, here it is, this dense on the outside, right? All this portion here is this solid hardened bone that is good at providing protection and support. Now the spongy bone that we see with all the trabeculi and struts on the inside, there's that epiphyseal line again, but all this spongy bone on the inside is lightweight. It provides tissue support. It also gives us resistance to stress from multiple directions, where compact bone really only resists stress in one direction. It's unilateral. Now on your slide, you're able to click this bone dynamics and tissue, which will bring you to an interactive animation. This will run through Wiley, but you have to be connected to the internet in order to access this slide. So have a look and watch this little video. So with this model, we're going to look at the osteon or the haversion system, point out some anatomy, as well as the trabeculae and spongy bone. Let's point out some structures. So we can zoom on in and look at our tree within a tree. So when we talked about tissues, we talked about bone and tissues, we talked about how the cross-sectional anatomy of bone resemble trees, concentric circle within a concentric circle, these lamellae within lamellae within lamellae. So what could we see? We can start here and see our central canal. You can see the blood vessels that are going through that central canal. And then look, we have these perforating canals or Volkmann's canals that are connecting these osteons, delivering nutrients. Now, the next thing to see is we have our concentric circle, ring within a ring within a ring. These are our lamellae. Now, one other thing to look at is that we have two other types of lamellae. We have concentric lamellae that make the ring within a ring within a ring. We have interstitial lamellae. These lamellae fill the spaces between osteons. They are remnants of osteons that were partially reabsorbed or resorbed during the process of bone remodeling. The third type of lamellae is outer circumferential lamellae, so we see them here. So it is what forms these outer plate-like structures that wrap around the entire bone, including the spongy bone. Now we're going to go back to our osteon. So remember that within those concentric lamellae, those rings within a ring, we have these depressions. So those depressions are called lacuna. So we're going to zoom on in here. So let's zoom in to that depression. So the cavity that this cell, and you can tell it's a cell because it has a nucleus, lives in is the lacuna. Now the cell that occupies that space is that osteocyte. Remember, the osteocytes are maintaining the matrix. And then we get these little perforating, or these little extensions off of that lacuna called canaliculi. Now these canaliculi supply nutrients, from blood vessels, they help remove cellular wastes, and they provide a means of communication between the other osteocytes. A few more things to look at are going to be these Sharpie's fibers. So we talked about perforating fibers or Sharpie's fibers here, and it's really what's connecting that periosteum to that outermost layer of bone. Now remember, the periosteum is made up of two layers, an outer fibrous layer and an inner osteogenic layer is what gives rise to those osteoprogenitor cells. Now if we go to the far side of our picture, we have our medullary cavity, and you can see that inside that medullary cavity, it is, at least in this picture here, it is lined with this spongy bone. How do you know it's spongy bone? Because of the trabeculae that we see. Let's look at the composition of bone matrix. So the extracellular matrix of bone is about 15% water, 30% collagen fibers, and 55% crystallized mineral salts. Now, these mineral salts right here are inorganic components of bone, and they include salts of calcium and phosphate, as well as hydroxyapatite. Now, since there are inorganic components, we also have to outline the organic components. So these collagen fibers, which are type 1 collagen fibers, are the organic or living portion of the bone matrix. The most abundant mineral found in the bone matrix is calcium phosphate. Calcium phosphate combines with other mineral salts, calcium hydroxide, to form crystals of hydroxyapatite. As the crystals form, they combine with other mineral salts such as calcium carbonate and ions like magnesium, potassium, sulfate, and fluoride. They end up being deposited into the framework, which is formed by those type 1 collagen fibers. They crystallize and the tissue hardens. This is called calcification or ossification. And it is initiated by those osteoblasts, those bone-building cells. Now that we have covered the anatomy of compact bone, it's time to cover and look at the anatomy of spongy bone. So what we're going to do is we're going to start on the left here and look at our trabeculae, our struts. All these spaces that you see is where red bone marrow is going to move through. Now we're going to enlarge into a cross-sectional cut of this trabeculae, of this strut, and look at how it's arranged. First and foremost, notice there is no haversian canal or central canal. All we get are these lamellae. And again, on the margins of those lamellae are our lacuna and osteocytes. So we still need those bone cells that are going to maintain this matrix. And again, we still have the canaliculi so that they can communicate. Now, another thing to notice is surrounding this strut, surrounding this trabeculae, are all of our osteoblasts. So all these bone building cells, they're aligned along trabeculae of new bone. And then look, right behind it is our osteoclast, our little Zamboni, that is going to come through, gobble up, and pave the way for these osteoblasts to lay new bone. So we talk about our skeleton. We're going to get into it in a little bit, but we talk about osteoclast activity and osteoblast activity and how much new bone is laid down a year. And roughly about 20% of our skeleton gets remodeled every year. We're going to finalize our comparison between compact bone and spongy bone by essentially looking at a table comparing the two. Now, again, the translation from our PowerPoint to explain everything's a little bit different, but our line for this table should pretty much extend here and then here, right? So let's look at one structure, osteons. Does compact bone have them? Yes. They stack along the long axis of bones. They're very strong when stressed from limited direction, and we introduced that before. That's key. These osteons, this compact bone, can only resist stress from limited directions. That's why it's along the length of the bone. Now, spongy bone, no, they do not have osteons, but they have trabeculae, struts, that's able to withstand stresses from many directions. So now here's the key. When we talk about where muscles originate and insert, they're typically at the ends of bones. So we're putting a lot of force, multi-axial, so multi-directional force onto these bones. So it makes sense to make them out of this spongy bone, this strutted, hollow, more flexible bone, because it is going to be able to withstand that stress from multiple directions. Now, location. For compact, we found it in the shaft and the outer surface of bones. For our spongy bone, we find it at the epiphysis and then towards the midshaft. Blood vessels. Compact bone, yes, it has a lot of them. Spongy bone, no, they do not. Compact bone, lamellae. Yes, they have lamellae. Spongy bone, yes, has lamellae. Canaliculi. Compact bone, yes, has canaliculi. Spongy bone, yes, has canaliculi. And the bottom one that you cannot see here is bone marrow. So compact bone, yes, has bone marrow, typically white or pink bone marrow, most likely lipid storage. Whereas spongy bone, yes, it has that red bone marrow that's making those cells for hematopoiesis, but there is no marrow cavity. So that compact bone has that deep medullary marrow cavity, whereas spongy bone, the marrow is between the struts, between the trabeculi. Blood and nerve supply to bone. So how do we get blood and nerves inside a bone to feed all these structures that we just got finished talking about? So we do it via periosteal arteries. So arteries and veins are going to move through similar holes accompanied by nerves. So they're going to enter the diaphysis through Volkmann's canals. These are going to be accompanied by a periosteal vein. So arteries will be accompanied by periosteal veins. Now a nutrient artery is going to enter the center of the diaphysis through a nutrient foramen. Now when we get into lab with bone terminology, foramen is always going to be a hole. So the nutrient artery is going to move through a hole in this diaphysis called the nutrient foramen. And the nutrient vein is going to exit via the same hole. Now the metaphyses and the epiphyses also have their own arteries and veins, metaphyseal arteries, epiphyseal arteries, and epiphyseal metaphyseal veins. The next slide is going to show us a picture so we can identify some of these arteries and veins. So let's have a look. Blood and nerve supplies of the bone. So we're going to start at the epiphysis. And we see we have our articular cartilage at the end, followed by epiphyseal artery, epiphyseal vein, and our growth plate, or closure thereof, the epiphyseal line. And then in the metaphysis, we have our metaphyseal arteries and veins, and then we have that main hole. Here's our nutrient foramen in that diaphysis, and the nutrient artery and vein moving through it. Now through the periosteum, we also get some arteries and veins, so we have a periosteal artery and vein as well. And then we see them moving into the medullary cavity. You can see how vascularized this bone is, which brings us to our next question. We will talk about fractures, but I want you to think about this. What is the first thing that's going to happen when you break a bone? Well, the bone's going to bleed. And the reason why it bleeds is because there's so many arteries and veins, nutrients, oxygen-rich blood being fed to these cells and these structures. This almost brings us full circle to the formation of bone. So we're talking about ossification or osteogenesis, so bone creation, right? So there's 4 ideal situations for which bone will form. So obviously during embryological and fetal development, so in utero, when you're growing inside your mother's belly, your bones are going to be laid down and form. Now, how we do this is a specific process that starts from a cartilaginous model. So we're talking about a model called endochondral ossification. So endochondral means within cartilage. So what type of cartilage? We should talk about hyaline. Okay, so we're kind of previewing what's coming up, but we have the space, so we figure we write it in. Now, when bones grow before adulthood, so this is pretty straightforward. You come out as a baby, pretty small, and those growth plates that are filled with cartilage are going to grow and grow and grow and grow, and you're going to get taller, and your bones are going to get longer and wider at equal pace. So this is until you hit puberty or until you're done growing. So this is bone growth before adulthood. Now, when bones remodel, so remember we said that our body remodels about 20% of our bone every year. So that 20% is laying down new bone. Now, when fractures heal, again, we could talk about different types of fractures and microfractures. So every time you say jump off a table or off a step and land on the ground. You're causing microfractures along the bones that took the majority of those impact, and it will initiate more bone repair, bone growth. So that brings us to our types of ossification. So we already outlined endochondral ossification. It's from this hyaline cartilage model. So in utero, our skeleton is this hyaline cartilage framework that it will eventually be starved and then replaced with bone. Now the next and second is intramembranous. So look at intramembranous within a membrane. So we're talking about bone that develops in a membrane. So again, we're talking about embryonic tissue. Now this is going to occur typically in flat bones where connective tissue is going to be replaced by actual bone. Let's focus on intramembranous ossification. We'll look at the general process of what happens and look at the step-by-step process that occurs to give us this actual creation of this type of bone. So number one, it begins with fetal tissue and the differentiation of osteoprogenitor cells into osteoblasts, which then will differentiate into osteocytes. So where do we see this? These are dermal bones. So the bones of the skull, the flat bones of the skull, the mandible, and the clavicle all form under this type of ossification. So growth begins at a primary ossification center. The cells are going to cluster together, they're going to become more specialized, and then as this process continues, osteoblasts are surrounded by matrix, this osteoid, and then differentiate into osteocytes, thus creating the spongy bone. Now as blood vessels invade the matrix and bone forms around them, so this is how we form these strut-like arrangements. So if you think of it like taking two plates and you flip them over and then put them together. So the bottoms of the plate, the hard part, would be compact bone, and then the inside where that hollow space is would be where all this spongy bone is formed. So let's get the next slide and look at the actual steps. So let's take this step by step. So intramembranous ossification gives rise to what we call, or what I like to call, membrane bones. So again, our flat bones, our skull and clavicles and mandible. So we start with the fibrous membrane of connective tissue. So we see that right here. We're starting with this connective tissue, right? So once we start with that connective tissue, osteoblasts form from mesenchymal cells, which are undifferentiated cells from which all connective tissue is formed. And you can see these mesenchymal cells laying on the outside. And then the development of these osteoblasts. Now, osteoblasts are going to secrete the osteoid. This is an organic bone matrix. Now, once that occurs, the osteoid is going to trap the osteoblasts. They become osteocytes that live in the lacuna after the osteoid becomes mineralized. This all starts at one or more ossification centers in the original membrane. The collagen fibers of osteoid not arranged in lamella yet. They're not arranged in those plate-like fashion. The bone that we see growing here, and you look at this picture here, appears woven. So we call this woven bone. Now, osteoid accumulates, forming trabeculi and enclosing all these blood vessels surrounding. The periosteum forms outside the woven bone by the differentiation of some mesenchymal cells. Now, trabeculi under periosteum grow together and form more solid bone. Now, later in development, the woven bone is replaced by lamellar bone during the process of remodeling, which continues until the bone gets to its final adult shape and size. And we can see that here, that lamellar bone forming on the outside. So development of the periosteum, the mesenchyme at the periphery of the bone develops into the periosteum. The next model we're going to look at is endochondral ossification. Now remember, this is bone growth from a hyaline cartilage model. This typically starts around 7 weeks of development. It continues up until about puberty, where the growing cartilage in long bones keep pace with bone growth. Now upon the onset of puberty, when sex hormones are released, cartilage is gradually replaced by bone in those growth plates of the metaphysis. Now, as bones grow longer and wider throughout adolescence, they keep pace, so they grow longer and wider together at a consistent pace. Now, timing of epiphyseal closure differs in individual. Now, we say, well, when does bone growth typically stop? Well, we put an age range to it. It's anywhere from about 22 to 24 years of age, but again, this depends on when that individual reaches puberty. Now we could put endochondral bone formation to steps. Now remember, endochondral ossification replaces that hyaline cartilage with bone in the developing embryo and fetus. So let's take it to steps. We start with the hyaline cartilage model. So we're starting right here. And it's going to be surrounded by a perichondrium. Notice we said perichondrium, not periosteum. So peri around, chondrium meaning cartilage. Now that perichondrium is going to be converted to the periosteum with the addition of blood vessels. Osteoblasts are forming under the periosteum. This all starts late in the second month at what will become the primary ossification center. Now these new osteoblasts start secreting osteoid. This forms a bone collar around the cartilage model. The bone matrix under that collar calcifies, which causes the chondrocytes to isolate and die. So what we're essentially doing is choking off that cartilage, those cells of the cartilage, of nutrients, allowing them to die. Meanwhile, the cartilage ends of the model sticking out of the collar are growing just fine. Now, around the third month of development, a periosteal bud invades the cavities forming under the collar. Now, the periosteal bud's going to have three things specifically. Artery and veins for supply, neurons, nerves, that's going to deliver osteoblasts and osteoclasts. Now, the osteoblasts are going to secrete osteoid around what's left of the cartilage-forming trabeculae. And this is going to be of the bone covered in cartilage. So this is early spongy bone. The osteoclasts start to digest this newly formed bone. So basically you have this collar, the cartilage under it deteriorates, calcifies, then goes hollow thanks to the osteoclast, so the cells that are gobbling up that cartilage. Above and below the collar, the cartilage is expanding. The collar expands too, so you get this lengthening bone with the lengthening hole and in its center and with spongy bone at the ends. So you can think of it like a game of cat and mouse, where the ossification is chasing the cartilage formation. So now what happens at birth? At birth, a secondary ossification center forms in what will be the epiphyses. So essentially the same process as above is going to occur, except we don't have a medullary cavity. Once the secondary ossification is complete, there's only cartilage at the articulation surfaces and at the growth plate between the epiphysis and the diaphysis. This plate is called the epiphyseal plate. Short bones only have a primary ossification center. Irregular bones may have several ossification centers, which varies a little bit different from this long bone that we just outlined. So this is how we get long bones. Now we can look at that actual growth plate and what's occurring within that growth plate. So how bone grows from when you're an infant all the way through adolescence. So we deal with, again, endochondral ossification, which is occurring in the epiphyseal plate of long bones as they grow in length. Now this is called interstitial growth. So when bones grow lengthwise, we're talking about interstitial growth. So this is lengthwise. And then when we talk about growing widthwise, we're talking about apositional growth. So interstitial growth is lengthwise, whereas growing by width, so wider, is apositional. Remember, lengthwise and widthwise keep pace together. Now let's look at some of these layers. So we go to the epiphyseal side. Okay, so we're talking about the end of the bone, the epiphysis, and we're going to work our way to the diaphysis, to the shaft. So we're going from the end of the bone into the actual, towards the shaft, towards the middle. So I'm going to give you a mnemonic to help you remember the zones. So we start here and we say, real people have career options. So I'll write that out for you. Real people have career options. And that O is going to stand for here, the developing bone of the diaphysis or ossification. So now let's talk about what's occurring within each and every one of these regions. So we'll start with the zone of resting cartilage. So in this zone, it's called resting because nothing's really occurring. This is unmodified hyaline cartilage. Now for the second region, the zone of proliferating cartilage, this is where the chondrocytes become active. They undergo rapid mitosis and start stacking in columns. Now this is influenced with the release of growth hormone, and when we do the endocrine system in AP2 or Anatomy Physiology 2, we'll go over this hormone, but at this point its name tells us what it's essentially doing, stimulating growth. Now for the zone of hypertrophic cartilage, this is a zone of maturation. This is where the chondrocytes stop mitosis and begin hypertrophy, so growing. And they do this by accumulating glycogen, lipids, and alkaline phosphatases. Now the next zone is called the zone of calcified cartilage. This is where chondrocytes undergo apoptosis. So if you recall back to cell physiology or cell biology, apoptosis is cell death. So the cartilaginous matrix begins to calcify. So we're replacing those cartilaginous cells with bone cells and replacing that cartilage with bone, which brings us to our O, our developing bone of the diaphysis, the ossification. So osteoclasts and osteoblasts form the diaphyseal side, breaking down the calcified cartilage and replacing it with mineralized or ossified bone. So we talked about interstitial growth lengthwise. Now we have to talk about apositional growth, widthwise. So bone thickens thanks to this cooperative action of osteoblasts and osteoclasts. So we take it into 4 basic steps. Number 1, we have these periosteal blood vessels with this perforating canal forming within a groove. And then here's our periosteum. Now what happens is these ridges in the periosteum create that groove for that periosteal blood vessel. Now essentially it's going to pinch, almost like if you think of a cinnamon roll where you pinch and roll, right? So number 2, the periosteal ridges fuse, forming a tunnel. Now that tunnel is lined with the endosteum. Now step 3, osteoblasts in the endosteum build new concentric lamellae inward towards the center of the tunnel, forming a new osteon. Now, for the 4th and final step, now bone's going to grow outward as osteoblasts in the periosteum build new circumferential lamellae. So again, we're making those plates on the outside of the bone. Now the osteon formation repeats as new periosteal ridges fold over blood vessels and start repeating this process to lay down more concentric canals, concentric lines, making the bone wider and wider and wider. So let's talk about bone tissue. It's constantly changing. We already said that we remodel about 20% of our skeleton per year. So we're removing old bone and replacing it with new bone. Now we know that exercise plays a pivotal role in bone health. Exercise stimulates osteoblast activity, which improves bone density. Now what happens on the flip side with inactivity? So inactivity tends to weaken bone. So what I usually tell people is, this is a good tool to tell especially older patients, is move it or lose it. You know, if you want good bone health and you don't want to suffer from degenerating bone, you should move. Exercise, walking, etc. all helps to stimulate osteoblast activity. The problem is when osteoblast activity is outpaced by osteoclasts. So what does that mean? Is that the bone breaking cells are working faster than the bone building cells. So bones become more brittle, and this is typically what we see with osteoporosis. Hormones play a pivotal role in both bone growth. Sex hormones like estrogen. So females tend to grow faster than males from puberty on because they have a surge of estrogen. Growth hormone, plays a role. Calcitriol, so we talked about vitamin D3 synthesis in the integument system with the kidneys. Well, here we are seeing that it's going to help the kidneys make that calcitriol or calcitol that's going to help manage the calcium storage in the bones. Thyroxine, which is a thyroid hormone which governs metabolic rate, and then again calcitonin and parathyroid hormone. So we're talking about two hormones, both from the thyroid, well, one from the thyroid and one from the parathyroid. So PTH is from the parathyroid, which are antagonistic hormones. So calcitonin sends 99% of the calcium in the blood, amino acid by accident, so calcium in the blood, to the bones, whereas parathyroid is going to pull the calcium out of the bones when needed. Let's look at some macroscopic changes of bone from infant to adulthood. So what can we see? We see in an infant, we see our little thin compact bone with our spongy bone in the center and a small medullary cavity. Now, we see the medullary cavity growing in width, bones formed by our osteoblasts, and we see some constant destruction. So what happens is we build new bone on top of the old bone, and we destroy with our osteoclast what previously existed. So if you were to take this right here and essentially put it into this new bone, you see the orange is what existed previous, and those osteoclasts destroy it, which make that medullary cavity now that much bigger. Now through young adulthood, we do the same thing. We're going to have the osteoblasts laying all this new bone, growing outward, and then the osteoclasts are going to dissolve that innermost cavity, which was the new bone in the child. Now for adulthood, the same thing's occurring. We're growing more outward, slowly digesting and breaking away the bone on the inside until we get a full epiphyseal line closure. Now in your actual slides, you have an active link, which will lead you to an interactive animation for bone growth and remodeling, a nice little video to take you through what we've talked about. Now remember, you must be connected to the internet and in the slideshow mode in order to run this animation. The last few things we're going to talk about with bone is fracture and repair of bone. So how we repair a bone once it breaks, as well as outlining different types of fracture. So typically a fracture is a break in a bone. There are many different types of fractures that occur, and we'll look at these in a little bit. Now the healing process involves 3 different phases, which occur in 4 steps. So the 3 phases are: 1, the reactive phase. So this is how the bone reacts upon that initial fracture or break. It is an early inflammation phase. Next is the reparative phase. So reparative sounds like repair. So this includes the formation of this fibrocartilaginous callus, which is first, and then that gets replaced with a bony callus second. Now, the last phase is the bone remodeling phase. And this is where that bony callus is going to be remodeled to more closely resemble the initial characteristics of that bone. But again, it's never perfect. So let's put it to 4 steps. So the reactive phase. So right away, and we alluded before that as soon as the bone breaks, it bleeds. So the bone starts bleeding and we get this formation of a hematoma, okay, almost like this big clot. Now for the reparative phase, that clot is going to be replaced by this fibrocartilaginous callus. So we're replacing and growing cartilage in place of that. Now remember, bones grow from a cartilage model. So now we have a reparative phase. So we're going to slowly remove and replace all that cartilage with new bone growth. But notice it is shaped pretty weird. It's shaped like that initial callus. The body doesn't like that. Towards its goal of perfection, it's going to want to make that bone resemble what the bone looked like prior to the break. So it's going to want to try to remodel those bumpy protrusions back towards an initial appearance. So we get that remodeling phase where the bone is slowly going to remodel itself to resemble, but it never goes back to 100% perfect. Now, 2 things to realize. 1, the bone is now here harder than it was before it broke, And you're going to get these little defects in the side where the remodeling process is not perfect, which is why if you take an x-ray of a bone, you could typically tell that a bone has been broken previously. Let's take a look at this table to look at some common fractures. So the first one is called an open or compound fracture. So as you can see from the picture, it's pretty much when the broken ends of the bone break through, protrude through the skin. The next is a comminuted fracture. This is when the bone is splintered. Look, you can see all the splintered portions of the bone. It can be crushed or broken into pieces at the site of impact. And smaller bone fragments lie between the two main fragments. Typically, we need surgery to remove or clean that affected area because of all those crushed or broken fragments. The next is a green stick fracture. So think of it like this. Why would it be called green stick? If you've ever broken off a branch of a tree, of a young tree, and that tree branch is really soft and bendable, and you try to break it, it never breaks all the way through like an older tree branch would. It kind of breaks through a portion and the other side's still intact. Well, this is what happens, again, typically in children. It is a partial fracture in which one side of the bone is broken and the other side bends. It's similarly to the way a green twig breaks on one side while the other stays whole, but bends in regards. This occurs typically only in children whose bones are not fully ossified and contain more organic material than inorganic material. Another type of fracture we can look at is an impacted fracture, where one end of the fractured bone is forcefully driven into the interior of the other. Another fracture is a Pott's fracture. So if you've ever rolled your ankle and maybe you roll it and broke your fibula, this is a Pott's fracture. It occurs at the distal end of the lateral leg bone, which is known as the fibula, which will also cause serious injury of the distal tibial articulation. One of the last fractures we're going to look at is a Colles fracture. This is a fracture at the distal end of the lateral forearm bone, the radius, in which the distal fragment is displaced posteriorly. Now we can put everything together and look at bone's role in calcium homeostasis. So again, we have a negative feedback loop where we have a stimulus. The stimulus is going to basically disrupt homeostasis by decreasing blood calcium levels. So now we're going to start getting into those hormones and those glands that we talked about on the previous slide. So when blood calcium decreases, we have a receptor. These are the parathyroid glands that are going to detect that lower calcium concentration, increases production of cyclic A&P, which will then release parathyroid hormone. Now, the output, the gene turned on, which increases the release of parathyroid hormone. The effect is that these osteoclasts increase bone resorption. And at the same time, the kidneys are going to retain calcium in the blood, excrete phosphate in the urine, and produce calcitriol. The response is increase in blood calcium levels. So again, this is if we're at a deficit of calcium in the blood. Here comes PTH that's going to talk to these osteoclasts and increase bone resorption, which will help free up some of that calcium. And then the kidneys are going to respond as well by retaining calcium in the blood, excreting phosphate in the urine, and producing calcitriol, again, which is going to help store the calcium in the bones. And then once we get enough calcium levels back to normal, we negate this system. So negative feedback loop. The last thing we talk about is aging and bone tissue. Now, from birth through adolescence, more bone is produced than is lost during that remodeling phase. In adults, the rates are about the same, so osteoblast activity equals osteoclast activity. However, in older individuals, especially postmenopausal women, because their hormone levels, especially that of estrogen, drop, they experience a decrease in bone mass. So basically what's happening is reabsorption is outpacing deposition, which means that those osteoclasts are outpacing the osteoblasts. So what do you get? Let's look at the scanning electron micrograph. Here's normal bone. Nice, healthy, struts are maintained, the bone looks good. But look at the osteoporotic bone. Look at all these holes. So these little osteoclasts are getting in there and eating and mitering their way, zamboniing their way through the bone, and the osteoblasts can't keep up with all that activity, and the bone becomes fragile, weakened, and more prone to breaking.